This video will go through how to graph an exponential function. When we think about an exponential function, we have growth or we have decay. The general form for an exponential function is f of x equals a times b to the x minus h plus k. This is the same h and k that we saw in our vertex form of a quadratic. Now when talking about growth and decay, the most important thing to look at is this b. Right, this b value. If b is greater than 1, we have exponential growth. If b is less than 1 but greater than 0, we have exponential decay. Exponential growth is when our graph or our curve is increasing at an increasing rate. So our curve is increasing a little slower, and then it starts to get faster and faster and faster at an increasing rate. Decay means it's decreasing at a decreasing rate. So it starts by decreasing really quickly, and then it starts slowing down, but it's still decreasing. So we have growth or we have decay. So our first example, y equals 2 to the x. All we're going to do to graph this is make a table. So we're going to have our x and our y values. Now when you try to think about points that you want to plug into an exponential, right, we have this 2 to the x. Okay, so whatever we plug in is going to be our exponent. So we want to think in numbers that are going to work nicely with 2. Okay, 1's going to be 0. We definitely want to know where our y-intercept is by plugging in 0 for x. So if we plug in 0, 2 to the 0 power is 1, because anything to the 0 power is 1. Then we might want to plug in 1, 2 to the first power is just 2. And then plug in 2, 2 to the second power is 4. But we also want to look on the left side a little bit. So if we plug in negative 1, 2 to the negative 1 power is the same as 1 over 2 to the first, which is just 1 over 2, or 1/2. Now if we plug in, the more negative numbers we plug in, the smaller our fraction is going to be, so it's going to be kind of hard to graph. But if we go ahead and plot these points, we'll have negative 1, 1/2, maybe 0, 1, 1, 2. Oh no. I just want to plot some points. Alright, and 2, 4. So we can kind of see our curve working out here. Now when we think about an exponential, we have to find our y-intercepts, we plug in 0 for x, and that's going to give us wherever it crosses the y-axis. To find our x-intercept, we plug in 0 for y. So we want to figure out what x value would make 2 to the x equals 0. Well, 2 to the 0 power equals 1, and if we go into the negatives, we start making a fraction, but we're never actually going to get to 0. We're going to get infinitely close to 0, but never at 0. So we have something on this x-axis called an asymptote. We represent an asymptote with a dotted line. Right, that's spelled asymptote. Asymptote. Alright, this is a line that the graph approaches but never touches. It gets infinitely close to this line but never touches. Alright, so we have an asymptote with our exponential because we can never actually reach 0 or go below 0. Alright, so then we'll connect our curve. We'll get really close to that asymptote but not touch it. And I couldn't quite make all the points. Started out promising. Alright, but this is what our curve looks like. If we think about the domain and range of this graph, if we think about where we have x values, well, it's never going to stop going to the left. It's going to keep getting infinitely close to 0. And it's never going to stop going to the right. We're going to go up to positive infinity. So our domain is all real numbers, or negative infinity to infinity. Our range, right, if we think about where our y values start, we don't have anything down here below the x-axis, and we don't start necessarily at 0, because we don't have a value at 0, but we start infinitely close to 0. So we're still going to say we start at 0, but this time instead of a bracket, we're going to put a parentheses because we don't actually have a value at 0. And then it's never going to stop going up, so it's going to go to positive infinity. So our domain is all real numbers. Our range is 0 to infinity, not including 0. Now we have y equals 1/3 to the x. Now the one we just did was growth because our b value was 2, which is greater than 1. Now our b value is 1/3. 1/3 is less than 1, so this is going to be decay. We're going to graph this the same way. We're going to make a table of values. Alright, a good pick is to plug in 0 because we always know anything to the 0 power is going to be 1. So if we plug in 0, 1/3 to 0 power is 1. Now, if we plug in 1, 1/3 to the first power is just 1/3. If we plug in 2, we have to square both the 1 and the 3 to get 1/9. So now if we plug in positives, we're getting smaller and smaller fractions. But if we plug in a negative 1, 1/3 to the negative 1, alright, anytime we have a negative, we flip. So this becomes 3 to the positive 1, or 3 over 1 to the positive 1, which is just 3. And if we plug in a negative 2, we're going to get 1/3 to the negative 2, which is the same as 3 over 1, or 3 to the positive 2, which is 9. So now if we plug in these points, we're going to have negative 2 to 9, which I think is right there. We have negative 1, 3, 0, 1, and 1, 1/3, which is somewhere right in there. Just like before, there's no value that we can plug in for x to make y equals 0. So we have an asymptote at our x-axis at y equals 0. So we mark that with a dotted line, and then we can connect our points to make our exponential curve. Just like with our other graph, our domain is all real numbers, negative infinity to infinity, and our range is going to be 0 to infinity with a parentheses. We're not including the 0. So if we look at a exponential that just has b to the x, right, our y-intercept is always going to be at 0, 1. Because if we plug in a 0 for our x, it just makes it become 1. The a, the h, and the k are what transform this graph, which we'll look at later.